This is the sixth in the short video series on the files within the Control101 toolbox to support state space methods. So why are we doing this? Because obviously state space methods are powerful and popular tools for the analysis and design of system behaviors, and therefore we need a dedicated section in the Control101 toolbox. This particular video is going to focus on dealing with multiple practical issues such as tracking, integral action, estimation, parameter uncertainty, disturbances and more, and show how Simulink is an ideal tool for supporting the analysis and modelling of such scenarios. So as ever, a reminder of how to open the files. Use the quick interface is the recommendation, and the particular files we're going to focus on here are the ones that have got Simulink in the title as shown at the bottom. So specifically, there's going to be three files which basically go through the steps one at a time, starting with basic scenarios through to the full scenario with integral action and observer and uncertainty. And as ever, it's more effective to do this through a live demonstration rather than talking. So let's find the editor. Here it is. So the first file, state space 1. So as ever, these files start with a little bit of discussion, but not a lot, because the focus here is really on the use of Simulink. So it's going to start by saying, okay, what is Simulink? How can you use it to do open loop step responses? And this is a very simple example, just to get students started, showing how you can define your data, and then Simulink will pick up the data from the workspace and it will run it, and then you can plot that data. So that's just a quick introduction to Simulink for those who aren't aware. But really the focus here is on how I use it in feedback scenarios. So you can see the first bit has a simple state feedback, and here is the name of the file. Now if you want to look at that file, you can just open it. So I'll just show you here briefly. Here it is, here's the file, and you can just ask to open that file using its name. You can save it, you can edit it, you can do whatever you want with it. And so now this Control Toolbox file shows you how I can actually put the code and utilize this Simulink file. So define my state space model, define my initial condition, define my signals which are coming into the system, define my controller, and then once I've got all the data defined, run the simulation and plot the solution. So you'll see it gives you a template here for how to use these Simulink files. So next, how do I introduce feedforward, which was discussed in the 5th video. So you'll notice again, if you want to, you can open the file. Here's the Simulink file. You can open it. You can edit it if you want. You can save it, do what you like. But obviously, this file exists within the toolbox. You can use as is if you want. And you'll notice that Simulink's actually quite powerful for understanding the key steps in the design. So there's my model, and here's my state feedback. Very, very clear. It takes the states, goes through the state feedback, produces the input. Here's my feed forward. Use a summing junction along with the state feedback to create the input. So how you implement your state space becomes really transparent if you start using these Simulink diagrams. Now we've added a disturbance here, which again you'll see in the diagram above, and you can see the impact of the disturbance, and you'll see that we are going to get a bit of offset. We can introduce parameter uncertainty, and again that's an advantage of Simulink. Very easy to introduce parameter uncertainty into the simulation, and you'll see you get offsets and the like. So the second file, what's the focus here? We're now going to start introducing observers. So again, a little bit of explanation. What's an observer? A picture so you can see the full Simulink diagram, and here what's clear is that you use the observer state to design the input. So you'll see the state feedback comes out of the observer, so that structure becomes really transparent, and then that input, once you've determined it, is sent up into the real system model, the process, and the process output comes back and is input to the observer. So the structural decisions and design is really clear when you use Simulink, and that's one advantage of using Simulink. So again, you can see the code is set out for you. define your system, define your controller, define your observer, define all the signals that you might need, the input signals, and then run your simulation. Okay, no need to define closed loop transfer functions, anything of that nature. Simulink will do it for you. And so now we've introduced the observer, we can have a non-zero target, we can have disturbances, we can do simulations with parameter errors and the like, and you can see we're going to get offset because we've not got proper integral action. So the third file, unsurprisingly, shows you how to introduce integral action. So again, here's the Simulink diagram, very similar to the previous one, where the main difference is you've got this little bit added here at the top, which is where you've introduced your integral action. Okay, and so again, some code examples, nominal case, and then let's add disturbances and parameter uncertainty. So again, you'll see the code is all there, nicely laid out, so you can change your numbers, change your state space model, change your uncertainty, change your disturbance, change your design poles for your observer, etc., etc., and then basically run your Simulink file and get your answers. So in summary, this short video has given a quick review of how you can use Simulink to support the design of feedback and estimation with integral action of state space systems.